Here I want to talk about what I think is the perfect derivative calculus final problem, or a really nice problem to put on a final exam, because it encompasses a lot of what you might see in a derivative calculus type course. You'll cover implicit differentiation, regular derivatives, and a good review of pre-calculus as well. Before we jump into the solution, I just want to apologize for the lack of consistency on the channel recently. I've been moving my chalkboard into a different room. Some of you might recognize the setup from some of my older videos on pre-calculus, and also I've been a little bit swamped because of some extracurricular activities that I recently joined, and those are coming to an end. So there should be some more stable consistency on the channel moving forward. Another thing that I want to adjust really quickly before moving into the solution is a comment on one of my videos recently that asked for where I get my problems. And honestly, what I do is I kind of just Google math contest problems, and then there's a really nice website that I will link down below that has a really nice condensed list of a bunch of different contest problems you can find. So that's one way I find them. Other times I find problems that I'm just coming across in my everyday life, such as this one. This one was one of the problems that was brought to me by a Calculus 1 student that I was tutoring recently. And other problems I come up with myself. So now that that's out of the way, let's jump into the solution. So here for part A, it asks us how fast the top of this ladder that I've colored in yellow here is sliding down the wall this way when the base of the ladder is 12 feet from the wall. So we'll say this x distance is the distance between the base of the ladder and the wall. So let's jump into the solution for part A, and then once we have that done, we'll move into parts B, C, and D. So first we want to find how fast the ladder is sliding down the wall. So our goal is to find dy over dt. So how might we do that? Well, first let's look at how x and y relate. And the ground, the wall, and the ladder clearly form a right triangle, with the wall and the ground forming this right angle here, which means that the distance from the ground to the top of the ladder and the distance from the wall to the end of the ladder here, as well as the length of the ladder itself, satisfy the Pythagorean theorem. So x squared plus y squared is equal to 13 squared. So here we can solve for y because we have the distance from the base of the ladder to the wall. That's 12 feet. So we'll have 144, that's 12 squared, plus y squared is equal to 169. But now 169 minus 144 is 25. So y squared is equal to 25. But that means that y is equal to 5. We won't worry about the negative solution here because y is a distance, so negative solutions don't make a ton of sense. Okay, so we have y, but now we need to find dy over dt. And again, we're going to use this equation x squared plus y squared equals 13 squared. And what we want to do here is take the derivative of this entire equation with respect to t. So the derivative of x squared with respect to t is 2x dx dt. Same with y squared, that's going to be 2y dy dt equals 0, because the derivative of a constant is just 0. In this case, that constant is 169. But now we can solve this equation for dy dt. So we'll move this whole term over and we'll have 2y dy dt equals negative 2x dx dt. So now we're pretty much home free. We can just solve this equation for dy dt, and that'll give us negative 2x over 2y, but that just simplifies down to negative x over y times dx over dt. But now we can plug in our numbers. We know that dx over dt is 5 feet per 2 seconds. I think I had this written as meters, but this should be feet. We know that x is 12 feet, and we know that y is 5 feet. So here we know that our number is negative 12 over 5 times 5 over 2, which is in fact negative 6. So this is our dy over dt value here. So now that we're done with part A, I'll go ahead and write that conclusion up here, and then we'll move on to part B. So now we're ready for part B, and that asks us how fast is the area of the triangle that's formed by the ladder, the distance from the base of the ladder to the wall, and the distance from the top of the ladder to the ground. How fast is the area of that triangle changing? And again, we want to relate the area to our known values of x and y. And I also want to point out that this is all occurring at this x value of 12 feet still. So let's jump into our solution. Our goal here is to find dA over dt. So how fast is the area changing with regards to time? But our area can be defined as 1/2 x times y, where x is the base of our triangle and y is the height. And while we could solve for the area at x equals 12 and y equals 5, we don't really need to do that here because we're looking for dA over dt. And when we take the derivative of this whole thing, which we'll do in a second, we'll find that there are no a's involved. So let's go ahead and take this derivative now. We'll have dA over dt, which is exactly what we're looking for. That's nice. Equals 1/2 times y dx dt plus x dy dt. But now plugging everything in, we'll have 1/2 times 5 times 5 over 2 plus 12 times -6. And so here we have, let's see, 1/2 times 25 over 2 minus 72. But that's going to be equal to 25 over 4 minus 36. But that'll be 25 minus 144 over 4. But that's going to be equal to -119 over 4. So this right here, -119 over 4, is dA over dt, how fast the area of the triangle is changing with respect to time. Okay, once again, I'll bring that up here, and I'll probably color code it in something different than blue, maybe orange or red, and then we'll move on to part C. So I went ahead and wrote our answer to part B right here in orange, and now we're ready to tackle part C, which asks us how fast is the angle between the ladder and the ground changing. So I'll go ahead and write this angle in brown right here, and we'll call it theta. So our goal here for part C is to find d theta dt, or how fast theta is changing with regards to time. And the equation I'm going to work with is sine theta, because sine is a pretty easy derivative to work with, and so sine theta here is equal to y over 13. And y can change. Y is a variable, but 13 is constant because that is the length of the ladder, and that always stays the same. But y changes as the ladder slides down the wall. So now we can take the derivative of sine theta, so that's cosine theta, but then we also have to attach a d theta over dt, and that's equal to dy dt times 1/13, which is the constant that was attached to y here. But here we have something really nice, because we have cosine theta, but we know what cosine theta is, because the adjacent to theta is x and the hypotenuse is 13. That means that cosine theta is in fact 12 over 13. And then dy dt we have right here, which is -6. So we have -6 over 13 here, which means that d theta dt is equal to -6/13 times 13 over 12. But that means that d theta dt is equal to -1 over 2, and this is radians per second. So this right here is our final answer for how fast the angle between the ladder and the ground is changing with regards to time. And that's enough for now.